On paper, the engine looked like an upgrade. A new boat, a clean engine compartment, a display panel that showed temperature, oil pressure, and hours, information older engines never surfaced. The sailor who bought that boat in 2008 thought he had made the sensible choice. In 2006, Volvo Penta began fitting its D1 and D2 engines with an electronic module it called the MDI, the Mechanical Diesel Interface. The module does not manage fuel. It does not control ignition. It has no authority over whether the engine runs once it has started. Its one job is passing data to a display gauge, but without it, the engine will not start. By 2018, Volvo had revised that module through 6 separate part numbers, issued a formal recall campaign covering every current D1 and D2 model, and one documented catamaran owner had replaced 5 MDI boxes in a single year, the first recall replacement failing in under 2 minutes. The sailors who never installed that module are running engines with 20,000 documented hours and no black box failures because there is no black box to fail. The question is how that split happened, who made the decision that produced it, and whether you are on the right side of it. Have you bought a boat and inherited an engine you never actually chose? Tell us the make and model in the comments. If this is the kind of forensic breakdown you want every week, subscribe to Yachts and Boats. The split between the engines that got worse and the engines that kept improving did not happen by accident. It happened because 2 different businesses made 2 different calculations, and neither calculation had reliability as its primary variable. The first calculation was made by the boat builder. When a production sailboat manufacturer chooses an auxiliary engine, the decision runs through an OEM pricing negotiation. The engine manufacturer offers a unit cost low enough that the boat builder's margin holds. The boat builder accepts. That engine becomes the default in every hull that leaves the factory. The sailor buying that boat did not participate in that negotiation. The reliability record of the engine over a 20-year ownership horizon was not the variable being optimized. The OEM unit cost was. That is not a conspiracy. It is a procurement process. But the downstream consequence is that the sailor who buys a production boat inherits the result of a negotiation between 2 other parties, conducted before the boat was built, with no input from the person who will live with the outcome for 20 years. Volvo Penta and Yanmar have both held dominant positions in production sailboat OEM supply Volvo, especially in European boat builders, Yanmar in North American ones. Of 24 sailboats evaluated in Cruising World's Boat of the Year assessment, 10 carried Volvo Penta engines and 11 carried Yanmar engines. The remaining 3 were split between Nani diesels, Honda outboards, and electric drive, a combined total that does not add up to one full Yanmar. The sailor buying a production boat is, in nearly all cases, buying the engine the builder selected under those conditions. The second calculation was made by the engine manufacturer. To understand why the MDI exists, you have to understand what Volvo Penta was trying to solve. Their D1 and D2 series engines use traditional mechanical injection pumps. The injection timing, fuel delivery, and emissions compliance all happen through mechanical geometry. No computer required. The engine runs the same way a diesel tractor runs. But Volvo's EVC system, their electronic vessel control network, runs on digital data. Instruments, controls, and displays communicate through a standardized protocol bus. To get the mechanical engine onto that bus, Volvo designed the MDI as a bridge, a small electronic module that reads the mechanical engine's analog signals and translates them into the digital format the EVC network expects. The module was mounted on the side of the engine's heat exchanger. A heat exchanger is one of the hottest, most vibration-intensive surfaces on a marine diesel. Every time the engine runs, the heat exchanger cycles between ambient temperature and operating temperature. Every cycle flexes the metal. Every flex cycles the solder joints on the circuit board inside the MDI. Nordkin Design, a Canadian marine engineering resource that published the definitive public analysis of MDI failure modes, documented the failure mechanism directly. Thermal cycling and vibration fatigue in the solder joints of the circuit board. This is not a hidden defect. It is the predictable result of mounting a circuit board on a surface that specializes in heat and vibration. Volvo issued the first MDI under part number 211-20710. The second revision became 212-61871. By the third, it was 215-11215, with revision 4 introducing 215-58939 shortly after. 5 became 22458-451, then 6 became 2259-4274, each issued to address problems the previous version created. The current version, and the one dealers now stock, is 23231607. 7 part numbers across 19 years. Multiple documented interim versions that performed worse than the versions they replaced before eventually stabilizing. One owner posting in the Nordkeen design comments section described receiving a replacement MDI that arrived already carrying a superseded part number, a recalled unit shipped inside a box labeled with the current number. The parts supply chain and the failure record were running on different timelines. The formal recall in July 2018 covered 8 engine families: D1 to 13F, D1 to 20F, D1 30F, D2 40F, D50F, D2 60F, and D2 75F. That is the complete current D1 and D2 lineup. The recall was not targeted at a subset of production. It was the whole product. A catamaran owner who posted in the Nordkeen design comments section described his experience. 2 D1 30F engines, original installation in 2009, 880 hours accumulated with no MDI issues. Then the recall campaign began. Between February 2018 and the date of his post, he had replaced 5 MDI boxes across his 2 engines. The first recall replacement failed in under 2 minutes. He was in the Caribbean. The Volvo helpline is in Belgium. The bypass fix, a $3 switch wired directly to the fuel solenoid and starter motor relay, was not documented in any Volvo publication. Sailors reverse engineered it and distributed it through forums. It works. Volvo did not publish it. There is a detail in the MDI design that does not appear in the recall documents. The MDI has zero control over the running engine. Once the engine starts, the MDI could be removed and the engine would continue operating normally. The module exists only to authorize the start sequence and relay data to gauges. A component with no operational role in engine function is the single point of failure that prevents the engine from starting. That sentence is the engineering history of the D-Series in one clause, which brings the question forward. What engine was being built while Volvo spent 19 years redesigning a module that should not have been necessary in the first place? Beta Marine was founded in England in 1987. Their entire product history is one decision made once and held consistently. Take the Kubota industrial diesel block and marinize it. The Kubota block was designed to run agricultural equipment in harsh outdoor conditions with owner-level repair. It was not designed for a dealer service center with proprietary diagnostic software. It was designed for a farmer with tools, a parts manual, and a local dealer who stocks the filters. Beta Marine discloses Kubota part numbers directly to owners. Those part numbers work at any Kubota tractor dealer in any country where Kubota sells equipment at agricultural pricing rather than marine pricing. Andrew Grokut, Beta Marine's chief executive, told Yachting Monthly in December 2021, "A mechanical system is safe and will not power down at the wrong time." That statement is not a marketing claim. It is a description of the design choice that every Beta engine embodies. No module that can fail and prevent the engine from starting, because no such module was ever installed. With proper care, a Beta Marine engine exceeds 10,000 operating hours. The part disclosure policy means the owner doing the maintenance buys Kubota parts at Kubota prices, not Beta Marine parts at marine prices. That distinction compounds across a 20-year ownership in a way the upfront price difference between a Beta and a Volvo does not capture. The Yanmar YM series, the 2YM15, 3YM20, and 3YM30AE made the same architectural choice. Mac Boring, the Yanmar US distributor, quoted 20,000 hours of serviceable life for the YM series in a boat owner course in 2008, a figure the company attributed to the mechanical injection architecture that has no electronics-related lifecycle ceiling. The YM series achieved EPA Tier 3 emissions compliance in 2009. No ECU required. Tier 3 through mechanical injection, geometry alone. The older Yanmar GM series, the 2GM20, 3GM30, and their variants, documents the same principle at even longer timescales. Fleet operators running 3GM30F engines in shoreboats made the same economic calculation year after year. Replace at 10,000 hours, whether the engine's needed or not, because scheduled replacement is cheaper than unscheduled failure offshore. A marine diesel mechanic writing for Practical Sailor documented what survives inside those engines: cracked pistons, salt water in cylinders, sludged oil passages, conditions that would have destroyed any engine that could not be rebuilt in a boat cockpit with standard tools. These are the numbers that do not appear on a boat listing. The Yanmar GM series is also documented as field rebuildable without specialty tools. The compression ratio on the GM series is high enough that the engine starts without glow plugs in cold conditions, eliminating a potential failure point that exists on every lower compression engine that depends on glow plug function to fire. A sailor who understands compression ignition can diagnose a non-starting Yanmar GM with 2 fingers and a gauge. The same diagnostic on a Volvo D series with a failed MD requires a part number lookup, a dealer phone call, and a part that ships from Europe. France's Nani and Spain's Sol made the same choice Beta made. Both use Kubota or Mitsubishi base blocks. Both confirmed to Yachting Monthly in December 2021 that they have no intention of introducing common rail injection on engines under 100 horsepower. The stated reason was not technical conservatism. It was fuel quality. In remote cruising grounds, common rail injection systems operating at pressures between 2,000 and 3,000 bar are sensitive to fuel contamination that a mechanical injection pump tolerates without damage. The engineer's job on a blue water boat is to survive variable fuel in variable conditions. A chief engineer with a Class 1 unlimited certificate, the commercial license that qualifies a person to run the engines of the world's largest ships, endorsed the Nani 38 horsepower engine in a sailing forum in 2023 with a 3-word assessment. These are bulletproof. Which engine gets called agricultural and unsophisticated at the dock? The Beta, the Nani, the Sol. The same engines with 10,000 to 20,000 documented hours and no electronic failure modes, whose parts come from a tractor dealer at tractor prices. The insult describes the advantage, which leaves Westerbeke. Westerbeke built their engines the same way Beta and Nani do. Take an industrial block, marinize it, sell it into sailboats. The Mitsubishi and Kubota blocks inside Westerbeke engines are mechanically similar to the blocks inside Beta and Nani engines. The underlying reliability architecture was identical, but Westerbeke made one additional decision. They did not disclose the base engine part numbers to owners. The same Kubota block that Beta Marine points owners toward at tractor pricing, Westerbeke sold through their own branded parts channel at Marine Pricing. Forum users who reverse engineered the cross-references described the practice consistently. Supply the engine to the boat builder at original equipment manufacturer pricing, then extract from the owner on parts for the life of the boat. That model has now run its course. The authorized US distributor for Westerbeke, Transatlantic Diesels, operating out of Hayes, Virginia, states on their current website, there are no new marine propulsion engines available. Westerbeke parts remain available. Marine generators remain available. But if you need a new Westerbeke propulsion engine for your sailboat, the production line is closed. If you own the boat Westerbeke powered, you are sourcing parts from a diminishing inventory, attempting to cross-reference a parts catalog the company deliberately obscured, or facing a repower decision that was made inevitable by the business model the company chose when it sold the engine to your boat builder. Now a word on where the dividing line actually sits, because not all Yanmar engines belong in the same category. The Yanmar JHCR series is a common rail engine. Yanmar calls it the most advanced common rail system available in the Sailboat horsepower range. The Bosch injection system operates at high pressure and is managed by an ECU. The Yanmar YM series, the 2YM15 through 3YM30AE, is not that engine. The YM series uses mechanical injection and has no ECU. It is the engine the 20,000-hour figure refers to. The JHCR series is too new to have fleet data at high hours. It may prove reliable. The mechanical YM series has decades of documented performance behind it. Those are not the same product and should not be evaluated the same way when the criterion is independence from dealer service infrastructure at sea. If you own a Volvo D1 or D2 and you sail offshore without a bypass switch, you are without a contingency for the single most documented failure mode on that engine. The bypass requires a standard 12-volt push switch wired between the battery positive and the fuel solenoid, with a second connection to the starter motor relay. $3. The community documented how to wire it. Volvo did not. The failure scenario the bypass switch addresses is not an engine failure in the mechanical sense. The injection pump works. The fuel system works. The raw water pump works. The batteries are charged. The engine will not start because a circuit board mounted on a heat exchanger has experienced one thermal cycle too many, and a solder joint has cracked in a location that cannot be inspected without removing the module. The engine is mechanically sound. The electronic interface to a gauge display has ended the passage. The sailor who bought that boat in 2008 did not choose his engine. His boat builder chose it for him under conditions that had nothing to do with his ownership experience, inside a negotiation he was not invited to. Over a 20-year ownership, the cost of that choice is measured in MDI replacements, recall notices, offshore bypass wires, and a parts room at the US Volvo Penta facility that one industry contact described as approximately 10 feet by 10 feet and mostly full of filters. The ledger does not lie. The complete reference list for every claim in this video is in the description below. Subscribe to Yachts and Boats. The full archive is there.